Section 6.4 is on page 264, talks about differential equations with discontinuous forcing functions. So the forcing function has been given as fixed e to the t cosine of t polynomial combination, right? Now, this function is really given as piecewise, and if I look at the graph of this, I notice that between 0 and pi, between 0, assume pi is right there. I'm scaling this as I see fit. Between 0 and pi, where this is t and this is h, that happens to be 0. So there's nothing there. And once I hit pi, I am at 1. Okay, the color didn't change. I can fix that actually. It picks up at 1. Okay, something's not right. What is it? Let's go with this color. Okay, there we go. And it's going to run all the way to 2 pi. And after that, it's 0 again. And of course, this trend continues indefinitely. Oops. This trend continues indefinitely. So, from this, I'm trying to figure out how am I going to write this. Well, I copy down my differential equation right there. This would mean y double prime plus 2y prime plus 2y equal, and let's see how we're going to write this. If I look at this function, excuse me, turns on at pi of t and shuts down at 2 pi of t. And that's pretty much what it looks like using the u function. Now, if I apply the Laplace transform on both sides, so part A, they say to sketch the graph. I did. This is A right there. Part B, find the solution of the given initial value problem. Well, let's see how this is going to play out and explain what really Laplace does. If I apply this, well, now I know that this is s squared f of s minus 0 times s minus 1. That's the y double prime. If I look at the plus 2, the Laplace applied on y prime would be simply f of s minus y of 0, which is 0. And if I look at the last component, which is the 2y, that's simply twice f of s. So, the right side, when I apply the Laplace on the unit function, that is simply, by now, I am comfortable with that being e to the negative pi s, and in front of this is a 1. That transformation of that gives me an s minus e to the negative 2 pi s, also divided by s because there's a 1 there. And now, this is kind of like what we just did. And if I really look, and something hopefully you're figuring out by now, that you're going to get literally what you see right there. You're going to get, if you factor f of s, you're going to get an s squared plus twice s plus twice plus 2. So basically, that's really what the characteristic equation look like if you really think about it. Now we have few terms loose on the side. Let's get those. I notice there is a negative 1 left. And if I look on the right hand side, when I apply the Laplace, well, I already did the negative 2 pi s over s. minus e to the negative 2 pi s over s. So if I do two things in one, that is, if I move the 1 over and divide by this, I'm really looking at f of s, which was the integral from 0 to t, remember, in section 6.1. That's simply e to the negative pi s over s into s squared plus 2s plus 2 minus e to the negative 2 pi s divided by s times s squared plus 2s. S is the worst letter for me. It always looks like a 5, so I have to really work at making sure that it doesn't look like that. And this one right here that moves to the right now is over s squared plus 2s plus 2. And now, the game now is figuring out 1 over s into s squared plus 2s plus 2 is what kind of a decomposition, and that's really what turns out simple algebra. Completing the square, getting a, all of that stuff. So we know this is a, and we know this is bs plus c. If I clear the fractions, 1 will equal a into s squared plus 2s plus 2 plus bs plus c times s. You could use the Book's method, but automatically, if I let s equal 0, I could figure out what a is. 1 will equal a 0 there, that's a 2. If you put a 0 there, that's going to be 0. Automatically, I know that a is 1/2. And I could now get a common denominator and set the system of equations. That wouldn't be bad because I know a, you'll find the rest quickly if you really like. You could also choose two different values of s if you like. Let s equal 1, let s equal negative 1, and you come up with two equations. I'm going to do, I suppose here, if I take those now and proceed with this being 1/2, I'm looking at 1 equal 1/2 s squared plus s plus 1 plus bs squared, distributing that in, plus cs. So 1 equal, if I look at the s squared, the s, and the constant, well, that's 1/2 plus b. That takes care of s squared. That is 1 plus c, and the number loose by itself is 1. So I know out of this that 1/2 plus b equals 0 since there's no s squared on the right. And you could see I could find those values very quickly and efficiently by finding one of those constants. And since there's no s on the right, 1 plus c must equal 0, indicating that c is negative 1. And there it is. I just figured out where this came from. So now I could rewrite the whole function as f of s equal, and if I take e to the negative pi s out of it, this is going to be, and I could take a 1/2 as well. 1/2, 1/2, make that a 2. That will make this a bit simpler. This will be 1 over s minus s plus 2 all over, by factoring the minus up front, s plus 2 over s squared plus 2s plus 2 minus e to the negative 2 pi s times the same deal over 2, 1 over s minus s plus 2 over s squared plus 2s plus 2, and just copy that down, plus 1 over, squishing it in there. That doesn't look nice. Plus 2s plus 2. So, now that I have it written in this form, I could say, well, in this case, let me go ahead and apply the inverse Laplace transform on this, but I need to make it matching the table. So e to the negative pi s is not going to change much. It's really this part I got to work at. I know that this is s squared plus 2s. I need a 1, right? Half of the middle number plus So if I make that plus 1, right? So maybe I should do that on the side here. Let me do that right here. If I take s squared plus 2s plus 2 and say that is s squared plus 2s plus 1 plus 1, that's really s plus 1 squared plus 1. And that will save me a bit of work right here instead of doing that several times. And now that you have finished that previous homework, hopefully you're very efficient at this. Minus e to the negative 2 pi s over 2 times 1 over s, again minus s plus 2 over s plus 1 squared plus 2 plus 1 over s plus 1 squared plus 1. That part is being squished all the time. I'm going to write a bit smaller to make it look nicer. So, if I really want to go back and use the inverse Laplace transform, I know what needs to be done. I have to make one more adjustment. And that is, if I really think about it, I need an s plus 1. That's s plus 1 plus 1, right? So I could say that's s plus 1 over s plus 1 squared plus 1 minus 1 over s plus 1 squared plus 1. And this is going to be a copy of that. So that would be minus e to the negative 2 pi s all over 2 times 1 over s minus s plus 1 over s plus 1 squared plus 2, plus 1, I'm sorry, I'm getting carried away there, minus 1 over s plus 1 squared plus 1, and there's that piece, plus 1 over s plus 1 squared plus 1. Now that I have this, I could apply the inverse Laplace transform on it. I could say, well, if I apply the inverse Laplace transform on this, I will get f of t, which is the solution. I'll talk about what that means in a minute. And let's get this straightened out. If I look at this right here, if I look at the table, and I'm going to show you the table really quick. First things first, if I take e to the negative t, awesome when that happens. If I take e to the negative t, that would make this 1 over s squared plus 1. And if I look at the table, s squared plus 1, there's only one of those. This was from last time. So 1 over s squared plus 1. S squared plus 1 is right there. So 1 over s squared plus 1 is really matching property 5. That's going to go back. In this case, it's a 1 squared, so that's going to be the sine of 1t. And I would like you to write 5 on top of it, telling me where you got this, where you got this from. Property number 5. And if I look at the rest, and let's see how that works. Plus, it's going to be 1/2. Let's see. This piece right here is going to give me u sub pi of t times. And if I go for 1 over s, I know that's a 1. And how do I know that? Okay. 1 is right there by property 1. This is all from last time. By property 1. So I'd like you to write 1 on top of that. This piece minus, if I take e to the negative t, that makes this really s over s squared plus 1. If I'm looking at s over s squared plus 1, I'm guessing that's 6. That's a cosine in this case of 1t. And this right here, if I take e to the negative t, that's going to make this again 1 over s squared plus 1. I just did that for this piece, and I know that's the sine of t. t. So this is by 6, this is by 5, and we know the drill. For this piece, it's going to be, oh, that's going to close, that's it. And the next piece is going to be actually minus 1/2 u of 2 pi of t times, and I'm going to write in, it's going to be again the same 1 minus e to the negative t cosine of t minus e to the negative t sine of t. And that should do it without the shift. Now I have to add the shift. I need to add more space. And to compensate for the shift, I would take this, instead of negative t, I'll make it negative t minus pi. Yeah, you know what? I squished it too much. You know what? I'll do that under. Okay, let's go ahead and leave that alone. And let me write the final answer. Of course, once you become really efficient at this, you could actually make it all one shot. So I could say f of t. This had no u function, so it stays the same. This is u sub pi of t over 2. What this is going to do, it's going to shift. You shift a constant, it stays a constant. But the t is shifted by minus pi on every single one of those. Cosine of t minus pi minus e to the negative t minus pi sine of t minus pi. And this right here is minus u of 2 pi of t over 2. And shifting a constant again stays the same, e to the negative t minus 2 pi in this case. I'm breaking that so you could see it. It's a bit messy to see in the beginning. Once you do a few of those, you will become better at it. I do want to point out one thing really quick. Since these are periodic, every now and then, and that's what makes this a bit more confusing, every now and then the book says, well, but the sine of t minus 2 pi is the sine of t, and they ignore the shift. I'd like you to keep the shift in. So I'd like to see those numbers listed every time you use one of these properties. Now I could show you where the shift is. The shift of u of pi happens to be right there. Every time you take a shift back, you pick up a shift in minus that c. That's always the case. U of c, and whatever the transpose, the inverse transpose is shifted by that c right there. The next problem on the list is problem number 4, and we're going to do the same thing. Well, this f of t, and there is t, they say to graph it. If they don't, you should graph it. This says this system turns on from 0. Assume this is a 10. It runs from 1. Assume again this is a 10. All the way to 10, that system is on. And from 10 and on, that's going to be a 0. Well, if I write this, this says y double prime plus 3y prime plus 2y equal f of t. I know the system turns out at 0. Well, 1 times u0 of t, remember e to the 0 is 1. That's why they write a 1. And it shuts down at u10 of t. And we apply the same idea. If I apply the Laplace on this, here I will get s squared times f of s minus s times 0 minus a 0. If these are 0, you're going to only get the f function plus 3 times f of s minus a 0 plus twice f of s. So if the initial conditions are all 0, this is very quick and easy. You simply get f of s times the characteristic equation. On the right hand side, when I apply the Laplace on 1, that's 1 over s, that is by 1. And when I apply it on the u of 10, that is e to the negative 10s. And there's a 1 in front of this, that's where the s comes from. And I could look this up in the table, and applying the Laplace on u, there it is. That's property 12. I forgot to mention that on the previous problem. I should have stated where it came from, right? That came from 12. Actually, it's right. Yeah, that's fine. Okay, well, let's see how this plays now. By the way, since I am here, let me mention what you did. You figured out the solution to this differential equation. Can you guess how complex it is to come up with such a solution using the traditional method? Finding these coefficients, e to the negative pi times s times a sine times a cosine, multiple of those, that will be really lengthy. So Laplace allows you to solve extremely complicated problems very efficiently and very quickly. F of s times s squared, that's a 0, plus 3, oh, there's an s there, isn't it? Yeah, 3s plus 2 equal 1 over s minus e to the negative 10s divided by s. So I get f of s to actually equal 1 over s, and I know this factors, that is s plus 2 into s plus 3 into s plus 1, you know what I mean, minus e to the negative 10s over s into s plus 2 into s plus 1. So again, the tricky part in all of these sections is how quickly can I figure out the partial fraction decomposition of such a fraction. That is a over s plus b over s plus 2 plus c, and of course you could put those in any order, it doesn't matter. Well, if I clear the fraction, guess what? I really don't even need to use systems of equations. Plus cs times s plus 1. It's not helping today. So here, if I let s equal 0, I'll find a. If I let s equal 0, I'll get 1 equal a times 2 times 1. So a is 1/2. If I let s equal negative 2, I'll find what b is. I'll get 1 to equal a negative 2, that's 0. b times negative 2. Negative 2 plus 1 is a negative 1. And if I put a negative 2 right there, that's a 0. So this is 2. b is 1/2 as well. And if I let s equal negative 1, I'll get c. That will be 1 equal a negative 1 there, that's a 0. A negative 1 there, that's a 0. That is c times negative 1, and negative 1 plus 2 is a 1. That makes c a negative 1. So basically, that's the whole problem right there. Once I get this, I could go in and say, well, f of s is actually 1/2 over s plus 1/2 over s plus 2 minus 1 over s plus 1. I'm going to double check these numbers to make sure that I don't make a mistake. You know what? Probably I'm better off factoring the 1 over the 1/2. That will make my life easier. That will be 1, that will be 1, that will be a 2. And if I take the 2 up front, again, a nice trick, just using simple algebra. And I'm just going to check the coefficients to make sure that those are correct. before I go on and wrap it up. Yep. And now if I apply the inverse Laplace transform, so I apply the Laplace, come up with the function, use the table, and now f of t will equal 1/2. In this case, by by property 1, this is 1. And all of these are going to use the same basic transformation back from 2. So with 2, that's going to be e to the negative 2t minus 2 e to the negative t. Here I'm going to get the same thing, but now since I'm a bit more comfortable with this, I'm going to get 1/2 u to the 10 of t. So shifting a number by 10, that doesn't change it, that's still a 1. But here, instead of getting e to the negative 2t, I'm going to get e to the negative 2. And instead of t, it's going to be t minus 10 minus twice e. Instead of getting a negative t, I'm going to get a negative t minus 10. And that would be it. That's pretty much the whole trick. And that would be my final answer. So what I did again, I was able to solve a differential equation by using Laplace transform, which is really integrating. You know what? Let me shift this down just a bit. I want it to look pretty. Okay. And now if I box it, that would be it. That's my final answer. And the homework is really pretty much kind of what we did. The homework is right there, just 3 problems. Make sure that you spend enough time on those and get them out of it.